Okay, that was all rather technical, so I think it would be helpful now if we looked at some simple examples of some Markov jump processes so we can see what's going on. So here's our first example, and it's given here by what is called a transition rate diagram, because this is the diagram that shows the transition rates. So whereas before we had transition diagrams, here we have a transition rate diagram. And it's the same idea. Any non-zero rates get put on the picture with an arrow, but notice that because you don't have a rate to yourself, there are no arrows from a state to itself here. So let's try and work out what's the generator matrix Q that goes alongside this transition rate diagram. Well, the key is to first do the off-diagonal elements, right? And the off-diagonal elements are the ones in the picture. So from 1 to 2, we have a 2. From 2 to 1, we have a 1. From 2 to 3, we have a 2. And from 3 to 2, we have a 1. Note that there's no arrow from 1 to 3, so that must mean that rate is 0, as in we can't make that jump. And similarly, there's no arrow from 3 to 1, so that must be a 0. And then what do we put on the diagonal elements? On the diagonal elements, we have to make the rows sum to 0. Remember, for P in discrete time, the rows sum to 1, but for Q in continuous time, the rows sum to 0. So rows sum to 0. So that must mean that the 1, 1 item is minus 2 to make the first row add to 0. The middle entry has to be minus 3 to make the second row add to 0. And that one has to be minus 1 to make the last row add up to 0. Okay, so what's the transition matrix of the discrete time jump chain, as in the probabilities of where we jump? And remember that we called the transitions for the jump chain R. And so this is discrete time, so this is the things we're used to. So the first thing is all the on diagonal elements are 0, because the jump chain can't jump to itself. And then after that we take Q, but we rescale it so the rows add up to 1. So if we look up here where we have 2, 0, well, in order to get that to add up to 1, we're going to have to divide it by 2, aren't we? So that will become 1, 0. Similarly, looking at the second row, we've got, obviously that's gone to 0, and then we've got a 1 and a 2, which add up to 3, so I'll have to divide through by 3 to get 1/3 and 2/3. In the bottom row, we just have a 0 and a 1, which already adds up to 1, so we don't have to do anything. So that's the jump chain and its transition matrix. And note there that the rows add up to 1, because that's our old friend, the discrete time one. Whereas Q, the continuous time one, the rows add up to 0. So let's think what happens here. Let's suppose we start at state 2, say. Suppose we start at x0 equals 2. Then what happens? Well, first we see this, right? That's Q22. So we have Q2 is minus Q22 equals plus 3. Q2 equals minus Q22 equals 3. Because remember that we put negatives down the diagonal of the generator matrix for reasons that will become convenient later. So this means we wait a time which is exponential with rate 3. So starting from our state 2, we wait for an exponential 3 amount of time. Okay, so once we've waited that exponential 3 amount of time, where do we move? Well, that is given to us by the transition matrix of the jump chain. So then with probability, WP, with probability 1/3, we jump to state 1. With probability 2/3, we jump to state 3. And remember, we can't jump to ourself because that's not jumping at all. So we wait an exponential 3 amount of time, then we go down 1 with probability 1/3 or up 1 with probability 2/3. Similarly, if we suppose the jump is to 1, let's say, then we wait an exponential Q1 amount of time. Q1 is minus that entry there, so that's plus 2. So we wait an exponential 2 amount of time. And where do we jump to? Well, that's this row here, the top row, and that says we automatically jump to 2. Then jump to state 2. And, we can keep on arguing like that. From 2, we wait an exponential 3 amount of time, and then we go up with 2/3 and down with probability 1/3, and so on. And that's all explained in that single transition rate diagram. Let's look at another example. This one's a bit different because we've got an absorbing state here. Notice there's no arrows coming out of it. So, what's the generator matrix for this? Well, from A to B, we have QAB, QAC, we have QBA, QBC. Then, from C, we don't go anywhere. That's 0 and 0. And so again, we have to make these rows add up to 0, because in continuous time, the rows add up to 0 in the generator matrix. So that entry there is Q, is 0, that's obvious. This one, I guess we could call that minus QB, where QB equals QBA plus QBC. And we could call this one minus QA, where QA equals QAB plus QAC. So, and again, we could look at what's the transition matrix for the jump chain. That's the thing we called R. So, remember that well, let's deal with the top 2 rows, which are the non-funny ones. The diagonal entries become 0. And the other ones, we have to divide through to make sure they add up to 1. So the QAB will have to be divided by QA, and the QAC will have to be divided by QA. The QBA has to be divided by QB. The QBC has to be divided by QB. So those rows all add up to 1 because of this thing here. But C is an absorbing state, which means once we get to C, we stay there forever. And so the convention is that we write 0, 0, 1 there. 1 for we always stay at C, and 0 for we never go anywhere else. I mean, it's kind of the dead end of the chain, right? We never jump again. But the convention is that you put a 1 in the absorbing state in its own column, and 0s everywhere else. Finally, we could think of our old friend, the Poisson process with rate lambda. Poisson process with rate lambda. So its transition rates are, well, as with all counting processes, the only transition or the only jump we could have in the Poisson process was going up by 1. Right, so you can have Q from I to I plus 1. Those are the only transitions we ever saw. And that just always happened with rate lambda. And Qij equals 0 for j not equal to I or I plus 1. Because all the other rates are 0s, the only jump you can make is going up by 1. So the generator matrix for that is, well, I plus 1 is just above the diagonal, right? So just above the diagonal, we have lambda, lambda, lambda going down. And everywhere we have 0s, 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 lots of 0s. And then what about the diagonals itself? Well, we've got to make the rows add up to 0, haven't we? Because in a transition rate matrix, the rows always add up to 0. So on the diagonals, we'll have to put a minus lambda. And so on. That goes down on the diagonal forever because it's like infinite. So that's how we can see the Poisson process as a special case of this. Note that the jump chain here is extraordinarily boring, right? Because we know where the jumps go. The jumps go from 0 to 1 to 2 to 3 to 4 to 5. So the jump chain is just, at every step, we increase by 1. So the jump chain for the Poisson process isn't very interesting, but that's its generator matrix.